Okay. Good afternoon, everyone. I'm happy to welcome you all here at the VIPER symposium and symposium of the Tetra project, the Vlaio Tetra project VIPER. I'm happy to show you the results of this research project in this afternoon. Okay. Now, first of all, let's have a look at the program. So we will start with an introduction that's already started by Toon Goedemé. I'm the project leader of this research group and of this project, together with my colleague Joost Vennekens. We started this project about 2 years ago. And I will give you indeed an introduction. Afterwards, as you can see, different researchers will give different parts of the results of the different sub-parts of this project. We will try to keep the timing as neat as possible up to this schedule, such that you have enough time also to network with each other, with us, and also have a look at the demos. Maybe you have seen that there are some demos here, 5 in total, are positioned next to the room here, such that we, in which we in real time demonstrate and hands-on demonstrate what the different results of this project are. There's one case, or two cases actually, we didn't demonstrate. We were not throwing drones in the air during the demo session here, and we will not let patients sleep in a bed, but okay, that's due to other reasons than the pure technical issues, of course. So indeed, we'll first have 3 talks and then a break, on which, of course, also coffee and other refreshments, it's not real enough refreshments, coffee, is it? Are offered in the foyer, as we call it. Good. Let's start, I would say. So this is the project we're talking about. As I said, this is a project we started in October 2016, funded by the, in that time it was still IWT, I think, now rebranded towards Vlaio. As you probably know, we, EAVISE, are a research group which main research topic is the combination of applications of vision and artificial intelligence. And in this project, these 2 fields come together in camera systems for safety and security. A very broad domain, but very interesting and very lively at the moment. So what is the general scope? Well, there are many cameras all around us, and many indeed keeping an eye on us or on other people and situations. But in many cases, as the top figure shows, these camera images are just observed by human monitors. So people in the monitoring room, in a control room, that just look at the images and see if something happens that shouldn't happen. Well, there is this drive to automate it. I think that's logical. Another thing is that sometimes images are only used after effect. After that something has happened, then people go to look at images of the surveillance cameras, for instance. So what we would like to have is a real-time reaction on incidents. And it's mostly incidents concerning people, so we need first a very reliable detection of persons in images. That's one component the vision part of our research group took care of. And a second part is we need a reasoning system that can decide if an alarm must be generated. In some cases it's quite simple, as you can see, the bridge example at the bottom left. Can we operate the bridge when there are people present on the bridge? No, that's just an if statement. But there are cases where the thing on which we have to react is much more complex, like shoplifters, for instance, and so on. So indeed, what are we starting from? We're not starting this research from scratch. We start from pedestrian detection algorithms, in which previous research projects also already have been achieved, and the results show very, very good results. And even during this project, new algorithms became available, as you will see in the next presentations. So the main task is running these in real time, such that we do not only have the opportunity to do an offline or after the situation occurred analysis, but during the running situation. Moreover, we are more and more looking to LWIR cameras, so cameras that take as an input not the visual spectrum, but long-term infrared spectrum, which is also called thermal cameras, so thermal radiation, heat cameras also. The price of them is descending steeply, so that comes with a lot of opportunities. And moreover, knowledge representation-based probabilistic reasoning, on which the second half of our group, led by Joost Vennekens, is very proficient, offers many potential to analyze all these situations. Let's see what we can do with that. Well, indeed, the first part, detecting people in a very robust way, is achieved here in, the main idea is the combination of these two cameras. So we have thermal cameras, here shown at the top. Yeah, you can see that the image is rather blurry. Indeed, resolutions are not yet up to par with normal RGB cameras yet. So based only on this, I cannot clearly identify if it's now people or other things that move in our scene. While RGB images at the bottom of this figure also give clues, but maybe indeed they're complementary, and such that we would like to combine the two in one detector. Second part is a probabilistic knowledge representation for the analysis of situations. So that's something my colleagues will also talk about. That's what we will do, and indeed, what we started to do 2 years ago. And so here is a list of project goals. This is a IWT or FLYO Tetra project, in which also companies are involved. Some of the people here present are representing those companies that were involved during the project, but of course the result is very interesting for all of you. And here you can see the goals. I'm not gonna read them all, but the most important thing is that we would like these techniques not only to be studied, but also to disseminate it towards the industrial ecosystem. And so that's why we all invented you here, to show you what the results are and to help you by adopting this technology. These were the companies that were involved during the project, that indeed gave us advice during the project, followed the research for the previous years in different meetings. I would especially like to thank, of course, Agentschap Innoveren en Ondernemen, FLYO, by supporting us financially, but also the companies did a small financial investment in this project. Of course, we were very happy to see that the companies were very active in this project and supplied their own cases, which we will indeed demonstrate during this afternoon. Who worked on this project? Well, about half of our research group. Here you can see all people that worked on it. We'd like to give the word to all of the people that worked on it. Give the mic today to them. Luckily enough, 2 of them don't work anymore with us, such that we have a we won't spend until this night by listening and talks. So indeed, you will hear all of these guys' results. As you see, you can see that indeed myself and Joost Vennekens are leading both parts. We worked for the entire project, starting from October 2016 until now, full-time on this, while the others sometimes worked only part of the time or short or longer period in time. Kristof was the only, indeed, that devoted all his energy to this project, so we'll see. Here a quick overview of the work packages we studied. We put in our application file, as you can see, okay, we did things in hardware and person detection, in the reasoning for an alarm system, but the main part, the biggest part, is evaluation and dissemination, in which we indeed worked on different user cases delivered by the companies that were following this project, on which we will see how far the techniques go. Here is an overview of the different application cases. I won't give results now, but during all the different talks, you will see different all of these application cases popping up with real results based on real images captured together with the companies. So we worked on safety on bridges. The idea is, and locks, the idea is that these things can go open and close, and better not that people are present on the bridges or locks in the meantime. So there we have to very robustly detect the appearance of people on the bridge. It's together with the Port of Antwerp and Waterwegen en Zeekanaal. The blind spot problem is also well known for trucks, for cars, but also for other agricultural and construction vehicles. That's also a very important case. We're also demonstrating that we don't have real trucks here, but we printed them out, as you can see, in, on scale 1 by 1, part of it. So just also to detect if people are present in the blind spot, yeah, an alarm must be given to the vehicle driver. One other case that was delivered by Fleur is about the analysis of behavior of people on around train rails. As you know, it's very dangerous to walk over the rail tracks. That's behavior we want to detect automatically. But also we would like to detect suicide behavior before it actually happens on the rail platform. Let's see how far we will get there. We captured, or we acquired real images with the Fleur cameras to test our algorithms out. One case was delivered by Alphatronics, a company in medical systems. They want to do patient monitoring in bed, so to see if the patients are still in bed or did they leave their bed. And so we also acquired images. We asked a student to sleep. And she was very good at that. So we'll show images. It's not this student, fortunately, but okay. Another case is drone surveillance. So we work together with a few companies working with autonomous drones, or working on autonomous drones. And one case that we would like to autonomously detect people in situations where they don't have the right to be, or situations or locations that have to be guarded. One last example is about shoplifting, so shop thieves. Here you can see Kristof taking, no, it's not you, just joking. Indeed, so that's behavior that is captured in surveillance images. but very hard to detect automatically, and there we'll have to add a lot of AI to see what behavior is exactly indicating that the guy is trying to take something away without paying, or girl. Okay, to wrap up, here's again the program. As you can see, I put the different images along with the different talks, so you can see that every of the different cases is at least once, sometimes more times than one, demonstrated in each of the talks. Most of them also demonstrated in the demos. Good, I would like to give the word to the first speaker, which is Maarten Vandersteegen. He works on the first part, the camera system. So how can we combine RGB and IR camera images such that we can go on later on. I will give a quick overview maybe to the next speaker, Kristof Van Beeck, who will talk about the person detection part. How can we detect people in those images? Wiebe then will talk about how can we implement these people detection algorithms in real time on embedded and small hardware. And after the demo, we'll see our student sleeping in Timothy's work. He used another person detection, or compared a technique he's using with the people detection algorithms before, but used something else which is even more powerful. Pose estimation. And then Kristof indeed will give an overview of the different reasoning techniques and abnormal behavior detection techniques together with personal ReID, which he will explain what it does. And Joost, Professor Vennekens, will give an overview, then a closing, and give also an overview of future research. So if you're interested in following us up, that's an opportunity. Thank you. I will give the word now to Maarten Vandersteegen.
Good afternoon, and welcome to the first technical talk. So I'm going to talk about thermal and visible camera calibration. The idea behind this is that we want to exploit the possibility to create an even better object detector by combining both visible and thermal imagery. This is one of the results by combining those two camera image types. I will be presenting the parts on how to align both images, because you could run a detector on first the thermal image and then the visible image. But there is a more efficient way to do this and to combine them in kind of an early fusion. And later on, Kristof will present detection results based on these kind of images. So at the right you can see an image. It's a bit prettified, let's say. So the thermal cam has a thermal gradient overlay on it. So you can see that red is warm and blue is cold. And then the visible spectrum that is appearing behind it is a bit edge detected. We did that just to let you see that the alignment is pretty good. So you might have seen the demo, the camera setup at the left, outside. It's basically a very cheap setup. We have Seek Thermal Cam. That's one of the most cheap cameras out there. It's only $500, and it has a quite big resolution for being a thermal cam. It's 320 by 240 pixels, and it has a field of view of 32 degrees. We combined this with a cheap Logitech webcam, which has an HD resolution and a bit bigger thermal field of view angle. We presented already these results in the previous meeting. What is new now is that we also tested this on a different camera. It's the Vliegtra V1. It's a real professional camera that is used within traffic scenarios, so at traffic lights to monitor people. What is not yet in the camera is that the registration between both images is not yet done. So you can get the thermal image, you can get the visible image, but they're not aligned, they're not synchronized in any way. The big difference between the previous setup is that the thermal cam is a lot smaller, but it has a wider angle. The visible one has a very big resolution and also a 95 degrees angle. And we'll see later on that also lens calibration is going to be very important here. So let's get to it. Why do we want to register both images? As I said, you could do it with two object detectors and then combine the resulting positions in some kind of way in post-processing. But early fusion, so aligning pixels from one image to the other one, has an additional advantage. And these advantages are that you only need one detector. You need an additional input channel, but most of the time this is much faster than using two detectors. And it often gives better results, which we have seen in literature coming back many times. And also an additional thing that you might not think of, but if you want to train a detector, you need ground truth, you need annotations, and those have to be made manually. It's a lot of labor, and if you have two planes, you need to annotate them twice. You don't want to do that. If they're registered properly, you can annotate them on the visible spectrum, and those annotations are also valid for the thermal one. So this is also less annotation work. So the more reason to do early fusion instead of combining them afterwards. So this is what I'm going to talk about in detail, a bit about lens calibration quickly. Then we're going to talk about the image registration principle. So how do we do that? How do we combine those images? We propose a procedure, a generic procedure on how to do this. And then we'll show a block diagram of a complete pre-processing stage that you can use to combine both images. So lens calibration, I guess most of you already heard about that. It's not that exciting, but it's needed because those image registration techniques rely on rectified images. So because of highly angled camera lenses, you get these barrel kind of effects on your images, and you need to compensate for that. The thing is that since we're going to do image registration, that we don't need other kind of calibrations. So no external or internal camera calibration is needed here. So we're only doing the rectification of the lens distortion. So here you can see two images. This is, by the way, taken with the Trafi 1 camera. So on the left top, you see the uncalibrated images. You can see that the door is quite not straight. Also, the line at the ceiling is a bit curved, and that's due to the lens. And if you calibrate it, we get this pin-cushioned version at the right. Also, the thermal camera, we can do that too. I'm not going to discuss how to calibrate a lens in the visible spectrum because most people know this. But I'm going to talk about a bit how to do this in a thermal spectrum. Normally, if you calibrate something in the visible spectrum, you have these calibration boards with a chessboard pattern, but that is not visible in the thermal spectrum. Some people use, let's say, an Edison lamp to warm up these boards, and then the black paint gets a bit warmer because it absorbs the light more, and the white surfaces, they're cold, so you can see a difference. But then you need to be very quickly, and calibration takes a lot of time, so it's better to create some kind of active calibration board which uses power to heat up certain elements. So we designed this kind of board with circular metal discs. They're painted white. So you can also use it for visible calibration. But the resistors glued with thermal glue on the back of them. So if you run a current to them, they will heat up, and you can see clear white dots on your thermal spectrum. It's also not easy to calibrate cameras with low resolution. You have to hold the board quite close. We needed many retries to be able to calibrate this kind of camera. And the best way is this type of board with an asymmetric grid. If you use a symmetric grid, we tried this and yeah, it just didn't work. The error was always too large because of you have only a few pixels, and if it deviates only a few pixels, you already get a quite big error. So your snapping of your detection of these circles must be very accurate. Okay. Yes. The black area is just wood with some kind of matte black paint. And yeah, the best thing is also to make sure that the discs are not too, yeah, don't transfer any heat to the back plane. Yeah, some kind of glue or double-sided, how do you call it? Tape, yes. That insulates a bit, and then we had a problem in the beginning that also the heat is rising, and it creates kind of drop formed that results in the thermal. So we had a problem with the detections there, but we made it a bit more robust afterwards. So that's a valid question indeed. So now about the image registration. So we start with 2 rectified images. And the idea is that if you have 2 cameras that partially see the same thing, let's say that object, the computer over there, and you have one camera with a small resolution, aspect ratio 4:3 or something, and then a big camera with a bigger resolution, different aspect ratio. And what we want to do is overlay them in a way that every pixel in the intersected region that is from your visible spectrum that is seeing the same thing as the thermal one. So that you get the same, you only see one object in the resulted image. So how do we do this? First we need a mechanism to reposition the pixels because we have 2 different pixel spaces. And the best thing to do is use geometric transformation. It's a mathematical term, but it's quite easy to apply. The formula is presented over there. Looks a bit, yeah, if you're not into math, it looks maybe a bit difficult, but it's quite easy. So the idea is, do you have a mouse pointer or something? Okay, so the idea is you have here an input pixel at position x, y, and we transform it to a position x prime, y prime. So how do we do this? The main thing is this matrix over here. This has 8 different values, and each value represents a certain degree of freedom. Rotation, translation, scale, aspect ratio. And by modifying these, we can reposition our image to the correct place. This type of transformation, we call it projective transformation because it's the best way to solve this problem like this. And these are the degrees of freedom you can create with this. So translation, you can rotate You can scale, upscale, downscale. You can modify the aspect ratio, a shear version, create a shear version of it. And also these two at the bottom support the keystone transformation. It actually is kind of a rotation, a projected rotation around the X and the Y axis. Okay, so now we have a tool to do this, but the trick is, how do we get these parameters? How to measure what parameters we should put in this matrix? This is done using correspondence tracking or finding. We have 8 unknowns, so we need at least 8 measurements to solve this system. And the idea is to find correspondences in the real world that we can track in both image planes. So if you have the computer and we find, let's say, 4 edges or 4 corners, and we find them also in the other image plane, then we know, okay, this pixel should be replaced to that position, that pixel should be matched to that position, that to that, and that to that. And then we can use some kind of function. You can, in OpenCV, for instance, it's find homography. You give that function these points, and it will calculate for you the homography matrix. So that's basically it. The trick is, how to find these points again. There are many techniques for this. You can do manual point clicking. I've done it. It's not that fun. And it's also not that accurate, especially if you have this 160 by 120 pixels, and you miss 1 pixel, you already get some error. So the best thing is to use a real object detector, which can position it much better. Most use object detection and tracking. So for instance, in thermal images, you can have a person walking by, a straight line, and then you track his head, for instance, and measure it at different points. And then you can use those points as your correspondences. And there's also a paper that did something about mutual information. We can also distinguish 2 different techniques for applying this thing. First, you have the static applying of your transformation matrix. The idea is that in a factory setting, you calibrate your camera, and then you make sure they don't move independently anymore, and then you can use it anywhere you want. Another type of technique is the dynamic techniques, and here we don't pre-calibrate it in the factory, but we just take 2 cameras, position them somewhere, and calculate the matrix at operation time. So if you're an object detector, first it starts with uncalibrated images, and then when it sees objects, it tries to find the object in one image, the object in the second image. You get 2 detection results, and let's say the distance between both points is a threshold or a measurement on how well they're aligned or not. And then an algorithm starts, and it starts to update the homography matrix until the threshold is low enough, and then you have calibrated images. But these things come with a cost, so you need more processing power to do this, so detections take longer. You need 2 separate object detectors, because you need to measure 2 different points. And also alignment is not guaranteed. So if, for instance, there are not enough objects, you're only relying on separate detections, and you're stuck with 2 uncalibrated images. And most techniques that use this are found only used on static scenes. So you have fixed camera positions and they never move again. With the static techniques, once they're calibrated, you can take a camera pair and you can move it around, you can tilt it, you can rotate it, whatever you want. Images are calibrated as long as you don't move them independently. So a bit more about the image registration procedure we propose. For most applications, I propose a static image registration technique. So you calculate it once in a controlled factory setting, use 10 or 20 correspondences, and then it's done and you can use it. It's also fast because at operation time, you only need to apply this transformation matrix for every pixel and you're done. So you don't need much processing power. So this is how such a scene would look like. On the left you have your two cameras on a stand, for instance, and a bit farther away, distance decalibration, you have a portable heated disk. We've made one. I'll show you later how it looks like. And the disk is portable, so you can move it around. And then you take a number of images. So on the bottom you see first camera 1 and then camera 2, the frame, and they both see the same disk. You put it in the middle, you put it in the corners, left, right, upper, center, upper left, upper right, and you take, you measure the points of each thing, and then you have a set of points. And also, these are the most important rules we came up with. Make sure that the distance between both cameras is as small as possible. This is for, most important for objects that are close to the camera. And then for objects that are far away from the camera, it's important that you calibrate at least the maximum distance where you want to detect an object divided by 2. So if, for instance, if you say, I have an object detector that follows persons, pedestrians, and you say, I want to be able to detect up to 30 meters a person, and beyond that, I don't care, then your calibration distance should at least be 15 meters. It can be more, but 15 meters is then the optimal point. And then the overlay error will be the lowest for all distances, because normally the calibration is a function of the distance, but if you do it like this, you can make, yeah, it's not that important to what distance you put the object to detect. This is the disk, how it looks like. So it's just an aluminum disk with 8 resistors mounted on it. You run a current through it using batteries, and you can move it around. Now in a real factory setting, you could create a wall with different points, and then you only need to take one image, and you have multiple correspondences. This is the output of our calibration tool. So it's not that controlled here because there are students walking around, but you get the picture. So I'm standing with this disk and I use like 10, 20 points. Basically this is a very simple detection. So I first ran a canny edge detector on it, then did a half circle transform, and then you use manual confirmation to see, okay, is a disk detected or not. But if you have a controlled environment, you can do this without manual confirmation, of course. Then we improved it a bit. This is the calibration output of the FLIR Trafi-1. We did a similar thing, but now we use ellipse fitting instead of circle fitting. The advantage of this thing is that if you stand with a circle a bit close, due to perspective transform, you get more ellipse viewed circles, and this works a lot better, especially because you need to, the alignment needs to be very accurate, and HUF will fit a circle onto that, but it will not be cleanly at the center of the calibration object. Again, about the distance, it's quite important. So left top, you see an overlay of unregistered images. You can see that the focal length is different. So the visible spectrum has a wider field of view. The thermal one has a smaller field of view. And if you then, for instance, register only at 1 meter, so calibration with the disk at 1 meter, and then you look at objects at 20 or 30 meters, you see that alignment is quite bad. And this causes this effect. But if you calibrate at a distance of, like, say, 10 meters, it's much better. And it works for all distances behind. So you can see at the bottom picture, for instance, a person standing at 30 or 40 meters, and the alignment is still very good. Okay, and this is how you would create kind of, let's say, a total pre-processing stage to merge those things. So we start with, for instance, a thermal cam and a visible cam. In this case, the example is also from the FLIR Traffic 1. So it has a thermal camera, it produces 9 FPS, and a visible camera with 25 FPS. So first you need a time synchronization. We did this in software. It's not perfect because, okay, they are not time synchronized, they're not frequency synchronized. So it's a bit trying to get the best out of it. If you really want to have fast-moving objects to be perfectly aligned, you need some kind of hard trigger or hard sync. But it's quite well. You will see later on a video of detections we run on disused images, and you can see that sometimes both channels slide a bit apart due to this time synchronization problem. So after the time sync, you have 2 synchronized images of 9 FPS. And then the thermal image first goes to an undistortion section that just applies the undistortion coefficients from your lens calibration. And then it goes to a remapping stage, and the remapping stage just applies the homography matrix. It's also a linear transformation, can be created in real time. For the visible spectrum, we do the same, only it doesn't need to be rewired. So the remapping pixels are remapped from the thermal image onto the visible one. And then you're left with 2 big pictures with the same size. The thermal one is just a small image in the middle with a lot of black pixels around it. And of course, we only want to see, for instance, the pixels that have both thermal and visible view. So we crop around a region, and then we can send those 2 pixels to a detector stage. This is the result. So on top you can see the uncropped system. So only the center has both pixels on it, and on the bottom it's the cropped one. And you can also see that, for instance, the tire is hot, and the head of the person is a bit warmer, and so on. Yeah, okay. Okay, this was my presentation about it. Later on we will see a bit more about detections on these kind of images, but this is presented by my next colleague. Thank you for listening.
I'm doing it so it's langer, zoals ik wil. Okay, so good afternoon, everyone. Does everybody hear me with this new microphone, even in the back? Yeah, okay, perfect. So hi everyone, I'm Kristof Van Beeck, one of the computer vision team members, and I would like to give some results concerning the research project in about 35 to 40 minutes, which means I won't go into too much technical details. I will try to give a high-level overview with a lot of images and videos and so on. So please, if you have any technical questions, you can always send an email or ask them to me during the coffee break. So this is what I'm going to talk about today. So I will first briefly explain how pedestrian detection works for people who don't have a huge background in computer vision. Then I will also explain how we can compare different methodologies in a fair manner. There are a lot of different algorithms, different methodologies. How can we compare them in a fair methodology? Then I will also discuss the challenges, advantages, but also disadvantages that these infrared images have. And then I will discuss 3 different methodologies that we've used extensively in our research project. We'll first start with DPM and ACF. So I'll briefly discuss how they work, the methodology. Then I will discuss how we've integrated thermal images, infrared images, in these existing RGB detectors. And I will also give the benefits on that. And I will also give results on a first use case from the company Fleur. Then I will discuss the third methodology, which is the newest one, new big trend in computer vision, deep learning. I will briefly discuss how that works. Of course, in 35 minutes, I won't go into too much detail again, but I want to give you a very brief overview of that. And then I'm going to give results on 3 use cases. Again, first on the Fleur dataset, and then the Alphatronics dataset and the Port of Antwerp application. Okay, so let's get started. How does pedestrian detection actually works at a very high level? Suppose we have this image and we want to detect the pedestrians, there's 3 pedestrians here. Well, we're first going to extract a number of features. That's the first step. And how do these features look like? It highly depends on the algorithm. So in this case, for visualization, we've chosen this specific representation. So features are just an intermediate representation which allows the computer to visualize the image in its own manner. In this case, we're using the oriented gradient, so we're going to look at the orientation of the change of brightness. Now, if we have this intermediate representation, we're going to run a model over it, and we're going to look for pedestrian-like appearances. For this, of course, we already need to have a model. An example is shown here, which is trained in an offline phase. And we're going to run this model over all positions in this feature space. So at each pixel position, we're going to run the model, which is quite computationally intense. Not at each pixel exactly, it's a step size in pixels, but let's say about every 4 or 5 pixels. Then we get a number of detections, as shown here. But due to the fact that we're going to evaluate a number of locations, we're going to have overlapping bounding boxes around the same person. So that's why we're first going to perform NMS, or non-maximum suppression, to eliminate these double detections and to only maintain the best detections, and then we get the final detection output, which looks like this. Now, each of these methodologies also returns some kind of score, some kind of probability measure, how certain that the algorithm is that this image patch is effectively pedestrian. And the score, indicated here with 50% and 76%, we can use that to define some kind of threshold to set a working point for our specific algorithm. Now, what about multiple sizes? Of course, pedestrians appear at different resolutions in the image. So we've solved that very simple by downscaling the image and using more steps, more different scales of the image itself. So, of course, that's again a little bit of a downside, because now we have to do the sliding window approach. We're going to have to look at every position, but also at multiple scales. So we have this huge scale space feature pyramid, which gets even more time consuming. But there are solutions for that, as we will see in the next few slides. As I've mentioned before, each of these pedestrian detectors returns some kind of detection score. So we can threshold these detection scores and, for example, keep only very good detections. Or on the other hand, we can put a very low threshold on that and keep almost all detections. So we can use this threshold, and by varying this threshold, we can set the accuracy of our application. If we only allow for a very high threshold, then of course we're going to make few mistakes, but we're not going to find all pedestrians. On the other hand, if we allow for a very low threshold, we're going to find almost all pedestrians, but we're also going to make more mistakes. And that's a trade-off. We need to develop the perfect algorithm which finds all pedestrians and even makes no mistakes. And that's quite challenging, of course. Now, how do we get such a pedestrian model? How do we get these kinds of representation of how a person can evaluate if there's a pedestrian in the image? Well, those are just learned in some kind of black box fashion. So we use hundreds, sometimes even thousands of images in two groups. We have the positive images, which effectively contain pedestrians, and we have the negative images, which don't contain pedestrians, so background images, as you can see on the bottom left there. And we're going to plug both groups into some kind of machine learning algorithm, sport vector machines, AdaBoost, neural networks, and so on. We train them for a number of iterations, and then we finally get some kind of model. This one is the deformable part model, and this one is another one called aggregated channel features. So that's, in a nutshell, how these pedestrian detectors actually work. Now, how can we compare them? Say if we have two different algorithms, or three or four or more, how can we compare them in a fair manner? Well, that's done as follows. So, of course, we have a training data set on which we've trained the model, but we also have a separate test set or validation set on which we're going to evaluate the different pedestrian detection methodologies. And this is done as follows. So we're first going to use ground truth annotations. So those are the dashed blue bounding boxes. And those are manually annotated, which means that a person, a human, has to draw the bounding box manually, and those are our ground truth data. And then we're going to look at the different detections that the algorithm returned. For example, the green one, they overlap with an annotation, which means that we're going to count them as being correct. We call that a true positive. Suppose we have an annotation which is not found. We call that's also an error, but we call that error a false negative. And finally, the last one is the red bounding box. So suppose our detector finds some detection which isn't actually there, that's considered a false positive. And this is done for all frames and for multiple thresholds. And they are visualized in some kind of mathematical curve. It's this one. You often see this in the literature. And those are the precision recall curves. I won't go into too much detail, but I just want to mention that the axes tell very important information. So the horizontal axis, the recall here, is some kind of indication about how many of the pedestrians we retrieve. If it's high, it's 1 or 100%, we find all pedestrians in the dataset. On the other hand, the vertical axis here defines the number of mistakes we make. That's the precision. If the precision is very low, let's say 0, then we make a lot of mistakes. All of our detections are not correct. If the precision is 100%, of course, we don't make any mistakes, all detections were correct. So effectively, we want to get to the top right point. That's our optimal point. If we have a detector there, that's perfect. It finds all pedestrians and makes no mistakes. Now, these curves, each curve is a different detector, and each point on this curve is actually a detection threshold. So indeed, if we have a low detection threshold, we're going to sit somewhere here. We have a high recall, we find a lot of pedestrians, but we also make a lot of mistakes. If we have a very high threshold, then we're in this upper region. We have a high precision, so we don't make a lot of mistakes, but we're also low in the recall. And that's the trade-off which I've mentioned. And we can compare different algorithms by looking at the distance to this top right point, or by simply looking at the area under the curve, which is often indicated in the legend. So a higher number here means that the algorithm is better. So these are the first type of curves. We also have a second type of curves, which we call the miss rate versus false positives per images. Again, not too much detail. The only thing you need to remember is that with these curves, it's in fact the other way around. So on the horizontal axis, we have false positives per images. So we want to have as few false positives as possible. So we want to go to the left there. And the vertical axis now shows the miss rate. So instead of the precision, it gives an indication of about how many of the pedestrians were actually missing. We want that again to be low. So for these types of curves, we want to reach the bottom left point. And again, we can use some kind of percentage measure, but this time it's not the area under the curve, but it's a specific point for one value of the false positives per image. In this case, it's this axis here. So in this case, lower value is better. Okay, so we're going to use thermal images. They have a lot of advantages. For example, we're able to visualize people even during low light conditions, during nights, mist, dusty environments, heavy rain, and so on. Another advantage is the fact that they offer inherent privacy. People are much more difficult to be recognized, of course, in these thermal images. However, an evident disadvantage is the fact that we now lose, indeed, discriminative color information. We only have a grayscale information, grayscale image of the thermal heat, so it's quite a little bit more challenging to perform, for example, person re-identification with these types of images. That's why often a combination of both RGB and long-wave infrared images are used. Okay, now with this in mind, with these backgrounds about different methodologies and how we can compare them, let's have a look at a number of pedestrian detectors that we've used and evaluated throughout this research project. Let me start with the first one. It's a deformable part model. I only show one slide about this methodology because it's quite old. It was from 2008. However, at that time it was state of the art, and even till about 2012 it was still one of the best performing detection methodologies. How does this one work? Well, we have a model, a rigid model, it's this one, the left image, of how a computer looks at a pedestrian. And then we extend this model using a number of parts. They are shown here, and these parts have a fine resolution, and they can be, for example, the heads, the arms, the legs of a person, and we allow for some deformation. So these are some kind of cost deformation functions of how these parts can shift relative to the root model. And this methodology works really well for highly deformable objects or for very specific viewpoints. And one of these example applications, as shown in the demo, the blind spot application, was developed with this methodology because of the specific viewpoint and the high deformation. Downside of this methodology is that due to the parts, it's slightly higher computational complexity. Now let's look at a more state-of-the-art pedestrian detection methodology. It's called ACF, or Aggregated Channel Features. This was developed in 2014, and it's very accurate and fast, even on low-end hardware, so even on CPU. You don't need a huge high-end GPU to get this thing to run in real time, even for very high accuracy results. Again, I'm not going to go into too much detail, but the main thing which I would like to show is that now we don't have parts anymore. We have a rigid template, but we're going to integrate or going to evaluate a number of channels. So we have a number of gradient channels. So each of these patches, we call them a channel. We have some LUV as well, so we're also going to incorporate visual information in that. So you don't have to know exactly how this thing works, but you just have to know that it's a very lightweight algorithm, which is state-of-the-art, or was state-of-the-art in 2014, and which achieves excellent accuracy results. Let's look at some applications that we've developed within our EAVISE research group. So the top left one is indeed also the demo, which is shown in the foyer behind me, and it shows the deformable part model for the detection of pedestrians and bicyclists in the blind spot zone. And it worked quite well at frame rates of about 8-9 frames per second on embedded hardware. So the main emphasis there was more on accuracy, also real time, but accuracy, of course, needs to be very high for these kind of safety applications. The bottom right is an application in which we've combined multiple pedestrian detector methodologies. So on the left, you can see a number of different colored bounding boxes. So we've actually run 3 different kinds of detectors. And on the right, you can see the combination of both. If I can restart the movie. A combination of both the 3, which yields very good accuracy. So these are 2 of the applications which we developed within EAVISE, specifically with these pedestrian detection methodologies. Of course, these only work on RGB. So the first question in the research project was, how can we extend these methodologies with infrared images? Well, effectively, it's quite simple. So, especially for the aggregated channel feature detector, what we did is we simply included an additional channel. Well, this is only conceptually, it's not a single channel, as I will show in a few slides, but that's the idea. We just plug in additional channels, which integrate the thermal information. Now, what's the problem? Of course, we need to retrain the model, so we have to have a lot of training data. Fortunately, we have some kind of publicly available data set, which is called the KAIST data set. It might also come in handy for a lot of companies. It's publicly available, and it consists of about 10,000 images, both in the RGB and the thermal domain, and they are perfectly aligned at hardware level using beam splitters. So indeed, we now have about 100,000 of images, both in the RGB domain, the long-wave infrared domain, and they both have about 100,000 annotations and more than 1,000 unique pedestrians. So this dataset offers quite some opportunities for training and evaluation, as we will show. So based on this dataset, as a first work package, so to speak, in the research project. We've developed the internal ACF framework, which was able to cope with these thermal images. So apart from the standard ACF, which I've shown before, which has 10 channels, we included 8 infrared channels, and then we did very extensive evaluation experiments. So I won't go into too much detail, but I would like to show on the next slide 3 of our main results. So again, we've tested a lot of different parameters. So amount of training data, different model size, resolution of the long-wave infrared images, and all of these details can be found on our website. But I would like to show a few takeaway messages with these 3 graphs here. Now, in this case, we have the false positives per image versus miss rate. So remember, we want to go to the bottom left. So in this case, the dark blue curve is the best one. What did we show there? Well, you can see 3 different colors. You have the green one, magenta or purple, and then the blue one. The green one is a model only trained on thermal images. The purple one is a model only trained on RGB, so only the visible spectrum. And the blue one is the combination. So this is when we combine both thermal and infrared together. And then we've evaluated that on different data sets. So this is one data set, the second data set, and then a combination of the first 2. What did we do? Well, we took the KAIS data set and we split them up into day images and night images. And these are the results for day images, and these are the results for night images. And indeed, we can see that during the day, our green infrared isn't that good. It's the topmost curve, so it's not that good. Our RGB model is quite good, but the combination is even slightly better. But specifically during the night, when we have very low visibility, we can see that the purple one, our visible model, works very bad. But we have a huge improvement about, if you look at the legend, about 30% by including these thermal images. So these were some quite nice results. Of course, they vary by varying the parameters, but you can view these experiments on our website. Okay, with these things in mind, so you now have a little bit of background about the methodologies and how we can compare them. Let's now look at different use cases and let's see how we've used these methodologies to solve problems that the companies gave us. And the first one is a test case by Fleur. So they gave us a data set consisting only of thermal images, so we don't have any RGB on this. And the goal was there indeed to detect abnormal behavior. So we want to detect a system or build a system which detects when people cross the train tracks. So we want to detect these kinds of behavior completely automatically. That was the goal of this research project. Let's see how did we do this. So first, some bit technical details on the videos. So the videos have a relatively high resolution for thermal images, 7 frames per second, and in total there were more than around 90 videos. And we split the task of detecting abnormal behaviors in 2 parts. The first part is what I'm going to talk about. So we first detect pedestrians, and we track them, and then we hand over these pedestrian tracks to the AI team, and they will detect abnormal behavior. So in this talk, in this presentation, I'm only going to focus about how we can detect pedestrians, how we can generate tracks, and I will not classify the tracks for abnormal behavior. That's done by Kristof Van Engeland after the coffee break. So let's see how we can perform pedestrian detection in these thermal images. As a first step, we try to use a quite naive approach. Of course, the camera is fixed, so why can't we use traditionally used simple background subtraction or background modeling techniques? Will this work? Well, of course, sometimes it works quite well. As you can see here, we have the 2 pedestrians and they are quite nicely separated. So we can just use these blobs as pedestrian detections. So that's quite good. This is the result with a mixture of Gaussian technique, by the way. However, this is just one example frame in which this methodology works quite well. We have a lot of problems in other frames. For example, occlusion, then the blobs are merged, or the camera is also auto contrast, which means that, for example, if a train passes by the train station, the auto contrast will change quite rapidly and will generate these kinds of images. So, of course, quite fast, we needed that we had to step away from these naive background subtraction techniques. Moreover, companies who use these techniques probably also know that they have a lot of parameters which need to be fine-tuned, number of Gaussians, length of memory, and so on. So we want to avoid that, of course. So that's why we want to retrain an appearance-based model specifically for this case. Therefore, of course, we need to have annotated data again. So therefore, we've annotated the most important videos. So we had about, of the 90 videos, we selected the most important ones, ordered from more to less important. So we, of course, gave more importance to videos in which effectively people cross the train tracks. And about 27 videos were labeled, resulting in about 25,000 frames and about 80 unique track IDs. And this dataset is also available on our website. So that's maybe also nice to see for some companies after you sign some small agreement, which isn't that strict. Okay, so now let's look at the results. So we've retrained a model on the labeled data using ACF, and let's see what this gives us. Okay, there will be a video in a few slides. First, let's look at some quantitative results. So now we're using precision recall curves, and you have to look at the blue one here. So again, this is the recall, this is the precision, so the best point is top right. So this is not perfect yet, but it's quite good already. So if you take one specific point, let's say for a precision of 90%, it's over here, and if you look at where the curve is, we have a recall of about 75%, which means that if we find 75% of the pedestrians, 9 out of 10 detections are correct, which is not that bad. Specifically, given the fact that we're only using thermal images, so we don't have any RGB information for this specific case. So that was not bad to start with, but of course, we further did some kind of small improvements. We did a number of improvements. I've selected 2 of them to be shown in this presentation due to time limits. And the first one is scene constraints. Second one is basic tracking to avoid missing detections, of course. So what did we do for the scene constraints? Of course, the camera is fixed. We can still use that knowledge, because if we assume a flat ground plane, then after a one-time calibration, we of course can expect that pedestrians at a specific position have a specific height. And for example, it's very unlikely to find a pedestrian in the air and stuff like that. So based on a calibration, we can perform easy rejections of detections if they deviate from a specific expected height. And this is done as follows. So we divide the image into a number of regions which have the same ground plane. For each of these regions, we're going to extract annotations. Then we're going to fit some kind of model through that. In this case, due to the viewpoint of the camera, it's a first-order simple plane. And then we can eliminate detections which diverge from the expectations. And of course, we now have some kind of tuning parameter, the allowed deviation. And we have to find an optimal point, but if we, I won't go into too much detail on this, but for the optimal point, we have an improvement of about 5% in precision. So that's quite nice with this very simple technique, which of course only results in very limited computational overhead. We just reject detections. We get some gain in accuracy. Second improvement that we've did, also that's quite basic, is tracking. I won't go into the mathematical details, but we're using simple Kalman filter. So the main goal is that we're going to track detections, and then if we miss one detection, we can still use the prediction of where it was based on data from the past. So again, we see some slight improvements, but let me show some video which is easier to interpret by us, of course. So this is a resulting video of the detections that we've achieved on ACF. You only have to look at the green bounding boxes. So the red bounding boxes are from a different experiment, which I did not explain in this presentation. So if you look at the green bounding boxes, then you see that it works relatively well. We don't have a lot of false positives. We have some missing detections, specifically for high deformation. So we already achieved quite good results for this use case. Now, what were the remaining challenges? Of course, there are always challenges to be solved. The detection isn't perfect yet. Of course, small pedestrians is often an issue, also low contrast, and also reflections. So in this case, our algorithm performs very well. It even detects this girl steps off the train, and even her reflection is detected. So that's counted as an error because it's a false positive. It wasn't annotated. So those are some open challenges to the fact that these thermal images reflect, of course. The heat waves reflect. So we were already quite happy with these results. However, there were always some improvements possible. And that's why we've taken a look at the new trends, which is called deep learning. Again, I will give a very brief overview. I won't go into too much detail, but I hope that at the end of this presentation you will have some feeling for how it works at a high level. Now, deep learning is a new trend. In a sense, it achieves excellent accuracy results, and it easily surpasses all other pedestrian detection methodologies that we've seen in the past. So it's indeed even better than ACF that we've seen before. And it's actually not that new. It already started in 1998, but only around 2012 we've seen this huge breakthrough. So this is an image of NVIDIA, by the way, which likes to coin it the deep learning Big Bang. So in around 2012, we've seen that we have a lot of big data. So companies like Facebook and Google and Amazon have a lot of images due to social networks and so on, which are also annotated. We have the fact that GPUs are becoming more and more affordable, and combined with these deep neural networks from the year 2000, around that, we have this huge big bang concerning deep learning, and we were now able to effectively use these algorithms in a reasonable time complexity. So how does this work? Very briefly, well, the main difference with ACF is that we're going to step away from manual feature development. So for ACF, for example, we had to manually define the channels. We had to say we're going to use 6 channels for gradients, we're going to use 3 channels for thermal, and so on. And we now step away from that approach, and we're going to let the computer give us the most important features. We're going to let the algorithm define them themselves. And how do we do that? Well, we define some kind of architecture. That's the network, the neural network. And it consists mainly of a number of important layers, mainly convolution layers, max pooling layers, and fully connected layers. Now it looks like this. And the main idea is that you just plug in an image, you feed it to a number of convolution filters. At the end, we sometimes have a fully connected classification layer, and then we get classifications out of this. And this works extremely well. Of course, there's again a downside. So the accuracy is very, very high, but we have a lot of challenges, I would like to call them, for these neural networks. So, as I've mentioned, the accuracy is very good, and we can detect many classes at once. I will show a very interesting and promising video in a few slides. We also have a lot of different architectures, not only for classification, but also for segmentation, detection. And we've seen that nowadays the trend is more and more towards using more and more layers. Now, what's the problem? You see this red hand. The downside is that the network, of course, needs to be trained. So let me go back one slide. For all of these convolution filters, they need to be learned. All the weights need to be learned. All the fully connected layers need to be learned. So the problem is we have lots and lots of weights and interconnections which need to be learned by the algorithm. It can vary from 100,000 to millions of parameters. So the problem there is that we need a lot of training data, hundreds, thousands of images, which we as a research group often don't have, of course, because they also need to be labeled. And we also need to have very high-end training hardware. I'm not talking about one simple GPU from, like, say, 500 euros or so, but I'm looking more at several clusters of them. So training of such a network often takes weeks and thus requires hundreds of thousands of images. So that's why it's very difficult for us to train them from scratch. However, the plus point is inference. So that means after you've trained a model and you want to run it on an image, that's quite fast, even on moderate GPUs. Now, given the fact that these methods achieve perfect or top accuracy, of course, we thought that it's very interesting to have a look at them at this specific research project. And now there are many different publicly available networks like Caffe, Torch, TensorFlow, PyTorch, and so on. We've had to select one, of course, and we've went for the darknet framework, which implements a specific architecture, which is called YOLO, or you only look once. And it works as follows. So it subdivides the image into a number of grids, and then for each of these grids, it's going to predict bounding boxes and also the class of the bounding box. And this method works extremely well and very fast. So this is an example video of my office desk. Don't mind the clutter. You can see that it's able to detect lots of instances like chair, mouse, keyboard, cup, TV monitor, even the potted plant it is able to recognize. a person, so by only looking at part of my hand, it is able to identify myself as a person, even at bad light conditions, laptop, keyboards, cup, books, and so it works really, really well. And this runs at about 50 to 70 frames per second on a mid-end GPU. So of course we were eager to see the detection results when applying this methodology to our FLIR test case, and this is what we did next. So we've tried them on just out of the box, just the vanilla implementations, and then we got these results. So we were already impressed by the fact that the network did not have seen any thermal images, yet it was still able to give relatively good results. Some false positives are also seen, but the results were quite good. What was the next step? Of course, we're going to fine-tune the network specifically for this dataset. Now, you may think that this is a contradiction to what I've said before, that the fact that we can't train these algorithms ourselves. Well, the solution there is to use transfer learning. And that's the holy grail nowadays of deep learning. We're going to use the fact that we don't need to retrain the complete network from scratch. So the network was trained on big computer clusters by other big companies, but we can reuse these feature layers. So we don't need to retrain them from scratch. We can assume that the features learned, which are able to detect pedestrian, might also be suited to detect other objects. And indeed, in practice, this is often the case. So we don't learn these weights from scratch. We can only slightly tune them, and we only retrain the weights in the fully connected layer. So by doing this, we only need a limited number of images, and training time drops down from several weeks to a few hours. And that's something that we nowadays use quite often in our research group. Let me see some examples on that. So for this specific case, for the FLIR dataset, we've kept the first 23 convolution layers, and then using only about 1,500 images, we trained this on a mid-end GPU. So this is in fact a gaming card, which we bought for 600 euros. Now it's already dropped in price, but again, there are better versions of it available. And training takes about 42 minutes for every 1,000 iterations. So one iteration is one pass through the network, and then backpropagation is performed with gradient descent to fine-tune the weights. Now, the next question, of course, would be how many iterations do you need? And again, I won't go into technical details, but we can have a look at these kinds of curves, these output curves, and then we can evaluate some kind of loss function and determine when to stop based on some stopping criteria. For this specific case, we needed about 10 hours of training. So that sounds relatively long, but we just turn on the training, do it at night, and then when we come back at office the next day, we have a new detection model. Now, also keep in mind that this one was the best. So after 14,000 iterations, we have at the best model, but still, even after about 2,000 iterations, which means, let's say, 1.5 hours, we already had a quite good model. You can see that there's some conversions at the end, so the last few hours are only about very small accuracy improvements. Let's see some resulting detections. So this now runs at about 60 to 70 frames per second on the gaming GPU, and it's almost perfect, as you can see. So let me play it again. You can see that we don't have almost any false positives, and it works really well. So let's look at quantitative results. As we plotted again on precision recall curves, remember that we need to achieve this top right point, and now we're almost getting there. So with this YOLO framework, we have this dashed red line, and we have accuracies when the precision is about 90%. We have a recall of about, let's say, 85%. So we detect almost all pedestrians, and we almost don't make any mistakes. Now, to our surprise, we would have thought that this curve would be even better, because if we look at the videos, we don't see any or not that many errors. So we've investigated that, and it seems that YOLO is even better than our curves show, because it's able to detect even occluded people which were not annotated. For example, in this case, this pedestrian is covered by this pole, here the same, and this one is not completely visible yet. So this is counted as an error. The red bounding box indicates false positives, and it's actually correct. So quite amazing technique. Okay, so then again, we did some improvements, ground plane constraint, tracking, and so on, but I'll skip that. Now, what about detection speed? I've mentioned before that it runs about 60 frames per second on a mid-end gaming GPU. Of course, many companies are interested to go to embedded, small size, low computational complexity, low power usage. And we're getting there as well. So this board is really quite popular. This is an example of the Jetson TX1. A demo is also running in the foyer with this board, and it's really quite small, so it's only credit card size. The demo that you see there is it's a little bit bigger board, but it's only peripherals. So the main core is really very small. And the standard YOLO runs about 5 frames per second on this Jetson TX1. So given the accuracy, that's really quite good, but of course it's a little bit away from real time. So that's why, of course, we can also use downscaled images of this network. We don't have to use all 23 convolutional layers. So therefore, Tiny YOLO was developed, which only consists of a limited number of layers, 15, which of course also trains faster. Accuracy is slightly less, but not that big of a difference. And now we achieve 12 frames per second on the Jetson TX1, or even 15 frames per second on the new generation TX2, as will be shown by the demo. And this board uses about 10 watts of power. So that's quite amazing. So please have a look at the demo during the coffee break. Okay, so this is an example video in which we now process 1 minute and 30 seconds of video in 9 seconds with this Tiny YOLO. So that's quite nice to see. It's 1 minute and 30 seconds which we can now process due to this Tiny YOLO on a mid-end GPU, and it only takes about 9 seconds of time. So that's quite some quite amazing results, of course. Okay, now the second test case was from the company Alphatronics. Toon already introduced the problem there a little bit. It's about patient monitoring in healthcare. So the company wanted to develop a system which can automatically detect when there's a person in bed and generate an alarm if there is no person in the bed after that. So if a person, for example, fell out of bed, they want to generate an alarm. For privacy issues, again, we're only going to use thermal images there. And the challenges there were, of course, ghost images. So in this left-hand image, there's a person which lies in the bed. In this case, she just left the bed, and then we have some ghost heat remaining. And of course, other challenges are due to blankets and so on. And we tried our different techniques. So we tried ACF, we tried YOLO on that, and we tried to evaluate how good these algorithms actually perform. So for that, we've again recorded a number of sequences for the company, resulting in about 1,100 images. And we were quite impressed with the results. So I hope you can see it, but this person is detected with a red bounding box. Same here, the same here. So YOLO is even able to detect these persons in very strange situations, or even when they are covered by blankets. It's not perfect yet. What are the main challenges for this case? Very specific poses like this one, or when people are lying under blankets, for example, like this one, then of course we don't have enough information to detect the person, but after only a few minutes, the blanket warms up, and then we're able to detect the person again. Let's look at some quantitative results. Now, the purple one here is the ACF. So remember again, top right is best. The purple one is our old school methodology, ACF. And then this red one here is our new YOLO. And then we can see that for this case, we have a precision of about 90%, at a recall of about 95%. So this is going towards almost perfect methodology.
Did you retrain the model that you used for YOLO on the images?
No, we did not retrain them for these specific images. Well, this one, the green curve, actually shows the YOLO retrained with thermal images, but from the KAIST dataset, so not from this specific dataset. So the red one is actually indeed the standard vanilla YOLO implementation, which indeed appears to be slightly better than the retrained on thermal, but we think that's due to overfitting on this very specific test case itself there. And then we see this blue curve, but that's a teaser for a presentation after the coffee break. Okay, and then the final test case was from the port of Antwerp. So credits for this presentation go to Maarten. I only explained them because it fitted better in the program. The goal there was to develop a safety system for lifting bridges. And so the company, or the port of Antwerp, wanted to develop a system which was able to detect if people are available, or are not available, but present on the bridge when the bridge opens. So we want to develop some kind of automatic alarm system. Now, for this case, we wanted to combine, again, both thermal and RGB. So the FLIR case and the case of Alphatronics were only thermal images. But for this case, we did the combination of both. And for this, Maarten recorded the datasets at the Siberia bridge with the FLIR Traffic-1 camera, which he's mentioned before. He had perfectly aligned images of that. And then he annotated about 50 tracks and had some number of training images, testing images. And with these perfectly aligned images, he was able to retrain the YOLO framework to cope with thermal images and RGB images as well. So how was this done? Well, of course, it's quite difficult to change the architecture of the network, because then we would need to completely retrain it, which was, as I've mentioned before, quite a big challenge. So the solution for this is, of course, the YOLO standard accepts 3 channels, R, G, and B. What we did was we replaced one of the channels with thermal channel. So we offer, or we integrate thermal at the cost of dropping some other information, hoping that the thermal information, of course, is more valuable. So we tried a number of combinations. So we interchanged the thermal channel with the green channel, with the blue channel, with the red channel. We did the same for LUV and HSV, so different color spaces. And then we tried, or Maarten tried different experiments, and then he found out that apparently this combination was the best. And so he went with that to evaluate the very specific case of detecting bicyclists and pedestrians on the bridges. Now, some curves again. These were the last curves of my presentation. So you have the blue curve here, and that one indicates the performance of the YOLO with thermal and RGB on the datasets of the bridge, the Siberia datasets, but trained on the other datasets, the CAIS datasets. Of course, he also performed some experiments on which he retrained it, again using transfer learning, with the images from the Siberia set itself, and then we can see these results, which again are almost perfect. So the green one shows the thermal, only thermal. The orange one shows only visible information. And then finally, the blue one shows the combination of both, which achieves very good results. And here is some demo video again, in which you can see the images. So we have the RGB overlaid with the thermal channel, and we can see the pedestrian detection. And even when a pedestrian is not completely visible, it's highly occluded, pedestrian detection still works quite well with a very high detection score. So we can see scores of up to 90%. So the algorithm is very sure that there is effectively a pedestrian at that position. Small scales works also quite well. So these were some very impressive results actually. And this is the other viewpoint in which we can also see that detection works quite well. Okay, so let me conclude my talk because I'm a few minutes over schedule, I guess. I've presented work of the computer vision team. Of course, this is not solely my work, so I would like to thank all people noted here. We presented an introduction to pedestrian detection. We discussed the different methodologies. We also gave some insights on how we can extend these methodologies with infrared images. And finally, we gave 3 use cases with extensive validation. So that concludes my talk. I hope it was interesting to most of you, and thank you. Wil je liever een andere?
Een andere?
Ik heb kunnen een die in ons lopen, dus gemakkelijk is het Is dat zo?
Ik denk het, ja. Ik weet niet. Dat.
Een klein beetje over. Zo wordt het. Zo 5 minuten later.
Okay, good afternoon, everyone. All can hear me. My name is Wiebe van Ranst, and I'm going to talk about a paper that was recently published by Niels Tertgat, a colleague from the University of Ghent, and me at the ICCV conference 2 weeks ago in Venice. It's about embedded real-time object detection for UAV warning system. So what's that about? That's what I'm going to tell you right now. First, what I'm going to talk about, I'm first gonna give you some information about the context that we created this application for, and then I'm going to talk about the hardware we used, then about different object detections algorithms we used, then our results, and then the conclusion. So first, the context. The idea here is to give firefighters or emergency personnel in general some kind of situational awareness in emergency situations. For instance, when a firefighter is called out to a fire, he does not know a lot about the building. It would be nice to give the firefighter extra information, for example, that there is a gas pipeline running on the ground, or that there is like a barrel of some dangerous gas standing near the building or something like that. Useful information for the firefighter. So using drones, we want to give the firefighter this kind of information. One obvious way to do this is to just manually fly around with a drone and look at the images and report the images to the firefighters. That way a person actually has to look at all the images, and it's quite labor intensive. So it would be nice if we could automate this process. So just automatically fly a drone around the scene, look for dangerous objects, also look in databases for dangerous objects like gas pipelines that are running through the building, and give this information automatically to the firefighters. One obvious setup that we could use to do this is to use some kind of centralized system, some kind of computer system that can maybe be in the fire truck itself, which communicates on one end with some kind of database that contains, for instance, where a gas pipeline is running, and also communicates with an embedded system mounting on a drone, and that way it can also control the drone, and on the drone itself there does not need to be any object detection. However, this link is quite fragile. If the drone loses connection with the centralized system, the drone cannot fly anymore or detect objections anymore. And it's also quite low in bandwidth, so if you want to transfer video from the drone to the centralized system, we need a lot of bandwidth. So the approach we actually took was to do the computation, the object detection on the drone itself. So for that we need quite a powerful embedded system on the drone itself that is able to do this, this object detection. This is an overview of what the firefighter commander actually gets to see. So you can see here that there's a gas pipeline running in front of the building, and that our object detection algorithm on the drone has found a person here marked as the little C. So as I mentioned before, we need to have some hardware that is able to run these object detection algorithms on the drone itself. So for that we need a lot of processing power. Because we would like to use some deep learning, we need a platform that is able to use CUDA accelerated applications, so it needs to have a GPU. It needs to be low weight, and it needs to have a low power consumption, because we don't want to put heavy things on the drone because it would also use more power. And one obvious candidate for it is, of course, the Jetson TX1. Kristof previously talked about this platform a little bit. It's essentially an embedded ARM platform that has a really powerful NVIDIA GPU, and it can be used for deep learning. It does not use a lot of power, and it's quite light, especially if you use only this breakout board on a smaller board. Then to the object detection part. We evaluated some object detection algorithms The first thing we tried was to use the RCF algorithm, also something Kristof talked about before. And after that, we also looked at the YOLO detector, which Kristof also talked about. To be able to make a fair comparison between the two on the NVIDIA Jetson TX2 platform, we also created a GPU implementation of the ACF algorithm, because the GPU on the platform is really powerful and the CPU not so much. So to be able to utilize the GPU, we created the GPU implementation. So first, some background about ICF. Kristof already mentioned some of this. So it uses a feature pyramid. There's some color information, the LUV channels in it. There's gradient, the magnitude of the gradient, and 6 orientation channels. And of course, it's a pyramid, so it has multiple scales. Then on every layer in the pyramid, we run a sliding window. So for each window, we evaluate, is there a person in this window, yes or no, and yeah, it also outputs a score, and based on that, we can know where the persons are in the image. Then what happens in each window? Kristof talked about the model ACF uses, or person detectors in general uses. Well, this is a kind of implementation on how you can implement this model, or how you can evaluate this model. It basically uses a series of decision trees. All these decision trees are, we walk through all these decision trees, which gives us a global score. So at the end of each decision tree is some score, and the result of each decision tree is added to a global score, and this gives us our final score, so the score of the detection in the image. This is really short in code. What this looks like really globally. So we first have to loop over each layer in each pyramid, in the pyramid. Then we have to evaluate each window in that layer of the pyramid. We have to evaluate each decision tree. And after that, we need to store the result in some global array. And this is important because it will come back when I talk about the GPU implementation. This line of code right here is also quite important. If at some point when we're walking through the trees, the score drops below a certain threshold, we can just stop and write that score to the global result. We don't have to evaluate all the decision trees further, which saves on a lot of processing time. So the features of the ACF, as I mentioned before, we use ACF features with the channels I also mentioned before. And this is actually about the GPU implementation. And the percentages you can see here are how much time is taken on every step of the processing pipeline to calculate all these features. So as we can see, you can see the histogram binning in this case took 27%, which is the longest, which is quite evenly spaced out. So this is the feature calculation. Then we also have to do the model evaluation. For that we use a hybrid approach. So one place where we can find parallelism in the ACF algorithm is obviously in the sliding window. So each window in the sliding window part can be evaluated in parallel. If you just do that, a lot of threads will idle on a GPU. So this works only when a lot of windows are active, when we cannot stop, when a lot of windows did not stop early, so in the early stages of evaluating decision trees. After that, we took a stage parallel approach where we evaluate each decision tree in parallel. And combining these gave us the best results, basically. So now for the deep learning detector, the YOLO version 2 detector, we also evaluated. Kristof talked about YOLO version 2 a little bit. So basically, it takes in an RGB image. It runs some convolutional layers on it, and it actually yields a grid of bounding boxes. Each cell of the bounding box is called an anchor, and for each anchor, each anchor actually generates a bounding box, a probability so a score for the detection, and also a score for each class. So YOLO is able to detect multiple classes. So basically a classifier which says, is this object a dog or a bicycle or whatever. In our experiments, we evaluated some different configurations of YOLO. We tried different video input resolutions. So the input video actually changed the resolution of the input video. Then we tried to change the input resolutions of the convolutional network. We tried two different detectors, Tiny YOLO and YOLO version 2, and also some different classes. And the big question we want to answer here is which configuration is best suited for our application. So now for the results. These are the results of all the algorithms we evaluated. On the left you can see YOLO version 2. So this is the average precision. So actually the area under the PR curve, Kristof also mentioned earlier. This is the YOLO version 2 detector with different input resolutions of the network. This is the Tiny YOLO detector, and this is ACF with different minimum scales on which we're looking. So as you can see, the YOLO version 2 detector unsurprisingly gets the best accuracy, and the higher the resolution, the better the accuracy. The Tiny YOLO and ACF are about the same. Then these are the results in terms of speed, and as you can see as well, on an embedded platform like the Jetson TX2, YOLO is able to get really high frame rates, even compared to ACF. And Tiny YOLO, of course, goes even faster. These are the results when we vary the input resolution of the video. And these are actually what you would expect. The higher the input resolution of the video, the slower all algorithms run. And this summarizes all our results. So on the y-axis here, you can see the average precision of each algorithm, and on the x-axis, you can see the frame rate which we got when we run the algorithm on the Jetson TX2. And as you can see, the YOLO V2 detector is actually the best one that we tried. If you want to go really fast, you might want to try Tiny YOLO on a low resolution, but of course you lose a lot of accuracy. And ACF is, at this point, ACF can keep up a little bit, but yeah, we can see that, especially on a platform that has a powerful GPU, deep learning, YOLO version 2 does better than ACF. So to conclude, we've benchmarked multiple detection algorithms on the NVIDIA TX2. We tried multiple configurations depending on the required frame rate and accuracy. Overall, we can say that YOLO version 2 is the top performing algorithm we tried, and also that it is indeed possible to run deep learning algorithms these days on a UAV thanks to hardware like the NVIDIA Jetson TX2. So this is a video of the different algorithms we tried. Here you can see YOLO version 2. This is Tiny YOLO, and this is both ICF run on a different minimum scale. Okay, that was it. Thank you very much.
Okay, Thank you. Thank you for all the speakers of this first session. I'm now glad to announce that the coffee break is starting, so we'll meet again here at 3:15. The coffee will be available in that direction in the foyer. The demos are of course here behind my back. Thank you for your attention already, and see you soon. Test 1, 2.
Ja. Hallo. Dank u. Beginnen? Ik heb geen idee. Ik dacht even dat dat Toon was, die leek er heel hard op. Ik weet niet waar dat Toon...
Je moet er daar.
bij Sharon aan het stoom daar?
Dat is een worden.
Je zit iets aan het tekenen, maar je mag gewoon jezelf aankondigen en beginnen.
Ah ja, omdat hij er misschien graag bij zou willen zijn. Of komt hij nog terug?
Die komt nog terug, die is gewoon aan het handtekenen.
Nu,
Ja.
daar.
Ja, want dat is blijkbaar liggend.
Ah.
Maar die zit hier, hè?
Ja.
Die is er binnen 5 minuten.
Ja, dat is goed. Oké. So, hello everybody. I hope you can all hear me. Is het aan? Hallo.
Ik denk het wel.
Ja, ik hoor me. Is het werkt dan?
Okay, so let's get started everybody with the second part of our workshop, symposium, with a presentation given by Timothy about post estimation.
Thank you, Kristof, for the introduction. I hope everybody can hear me because it's is it loud enough? Okay, thank you. So I'll be talking about pose estimation and using it for various applications, mainly in this case for patient monitoring for the VIPER project that was briefly explained by Kristof Van Beeck earlier. First, a little overview. So I'll be comparing a pose estimator with a person detector. What is the difference and why should you consider using it in your application? Then a little bit about general pose estimation. What is it and how is it used? The open pose detector that I'll be using, actually it's estimator, so that's a little mistake I made. Then in the case of Nele with Alphatronics, there we have the thermal pose estimation. So I will be investigating the use of pose estimators on thermal imagery and a little demo video and results and to conclude in conclusion. So first, what is a person detector and what is a person estimator, and mainly what is the difference between them? So as stated before in the presentations, a detector will mainly detect people and give you a bounding box around them stating this is a person with a a score that contains of the confidence, sorry. While a pose estimator gives you a lot of more information. As you can see on the two ballet dancers, there is a skeleton drawn upon them with points consisting of its pose, hence the name pose estimator. On the right side you can see a more detailed representation of these points. So you can see that we have 18 points concluding them. So how can you achieve these points? That's the main question of today. And therefore we have like two methods, probably more, but two to the main category. Sorry, I'm a bit nervous. So the first category is the top-down category, where you have a sequence of first detecting a person, then you continue by looking at the person and detecting arms, legs, torso, and further to the elbows, the knees, and you go down in the sequence. This can pose a problem, mainly that you have an early commitment to the first step. Suppose you only have part of a person, which is not enough person for you to conclude it is a person, then you don't look for the other parts, the arm, the torso, and the legs. So if your person detector fails, the rest will also fail. A second method, category, is the bottom up, where you go the other way around. You first detect all the parts, the separate ones, like your elbows, your knees, your head, points, your eyes, your ears, and then you try to combine them to have the pose that I showed you before. So here you can see two people where we took 3 pose points, anatomical points, the elbows, the arms, and the poles, and the shoulder. And with a little bit of imagination, you can see that it poses a problem. How can you combine them? You have 6 points and you have, a lot of possibilities. Which point contains a connection with the other point? So when you think about this in a higher amount of people, multiple people, then this is a NP hard problem, because the more points you get, the more complex the problem gets. And here you see 3 points of 2 people, but you actually have 18 points to estimate. So making it a large problem, and you want something real time, so you have to make decisions fast. The work of Zi Xiao, as mentioned on the bottom, actually solved this by using some techniques, which I will go further on in detail, by using part affinity fields and some knowledge that in the most of the cases, your knees are connected to your feet and to your hips, but not to your arms. So there's some points between them. Combining that with part affinity fields, which I will explain later, you will get a robust representation. So the detector the estimator, that I used is the Open Pose framework, which consists of 3 publications and uses 2 models. So we talked about convolutional neural networks before in the installation, or mainly known as deep learning networks. And this framework uses 2 separate ones. The top one for the part confidence maps. So that will give you a confidence, a score in the form of a distance, how further away from the point, how lesser the score will be. So kind of a heat map. For each separate point. So in the case of 18 points, we get 18 different confident maps. Apart from the confident maps, we also get the part affinity fields, which actually follows the trend of the image. So how do lines exist in the image? For an arm, you can see that it gives you a vector which is going in the same direction as the arm part. By combining those 2 neural network informations, you can actually estimate that this part with this connection trend from the part affinity model will actually consist of a connection and not this one. Combining both of these networks, you can get the pose estimation for multiple people at a fast pace. To use this, they have trained 2 models. In this case, this is the COCO dataset by Microsoft, where they just annotated all these key points for the confidence map model and trained it in the hope that something came out of it, and they presented a really good presentation. And the other one is, in this paper, is actually the MPI dataset, which is more specific to poses, consisting of more information. Well, since I stated that this is both datasets before and we used the vanilla pose estimator, we wanted to see if this estimator also works on thermal imagery, but without any retraining, since the data is here very extensive and we don't have transfer learning techniques yet to transfer learn them. Mainly the part affinity fields is a problem there yet. So maybe in the future that will be an option. So will this work on thermal imagery? Well, why not just try it visually? That's what the fun part of research is. If you don't know if it works, then just try it. And you can see that just by stating no results visually, you can see that actually something comes out of it. And not gibberish, but actually pose estimations on thermal images without many mistakes. Sometimes it misses it. So you see here that people have to be close by before it actually detects it, but it works quite nice, no? So we didn't retrain images or the models on thermal images yet. And the detection score actually is comparable and equal to the RGB field and the thermal field. So we don't have a big difference in scores for the points, separate confidence maps. And state that this is a low resolution image. So if you see this image, then you can think, yeah, it's quite big, it's easy, but actually it's only a small image, stated by my colleague Maarten, who presented me with these images, by the way. Another detail is that this runs on 8 frames per second on a gaming card, an NVIDIA 1080 Ti, which is quite nice if you think about it. For the case where we studied the patient monitoring, we actually have images of a person lying in bed, Nele, our master thesis student, and we wanted to see if the same model will also work on this kind of images, just visually. And again, we see that the ghost image remains a ghost, and when the person sits in the bed, partially, the pose estimator is actually capable of finding a certain pose. To specify on the left side, the right side, we actually have the confident maps for every point separately. So here we see no points, meaning no pose, but when she turns on her back, then you see each point separately, the confidence map. So it actually works really fine. So afterwards, because visual, that's really interesting, but it's not just to use the visual. Yes, it works. We actually have to pour it into some kind of numeric comparison. And that was this graph presented by Mr. Van Beeck before, where he already mentioned the teaser, where we have the ACF and the YOLO detectors, trained and not trained, the vanilla version. And then we put our own results in the open pose as the blue line on the top. Note that it gets a higher precision, mainly consistent of just not 100%, but stops abruptly at 88.22%. Why would that be? Mainly because a pose estimation is, what is a pose? And internally in the pose estimator, it determines a pose early on. So if it says, I have not enough parts, or the parts don't consist of a pose together, we will not print it out as a pose because the points don't work together. While the previous methods will actually look for a model and a distance, how much variation or distance is there between my model and the current box where I'm looking for. This is a small presentation, so I will continue with my conclusion, where you can see that we have a high precision of 100% at a frame-by-frame detection recall of 88.22. Possible improvements there is to actually use a temporal filtering, meaning that since we have video, we don't look at each frame separately, but the person who's laying in bed actually stays in bed. There's no teleportation device yet. So we can just filter it out over the time. Or we can use a different camera perspective. Now we have a top-down perspective where we lose the person when she goes up and steps out of it, since we only see the point of her head. So if we use a different perspective, maybe the results will improve even further. And strangely enough, we have no false positives. Mainly the thermal ghost that remains, the heat on the bed, will not be presented as a person estimated. On the videos, you can see actual other applications where we can use pose estimators for. On the left bottom side, you can see a tennis court where a person is playing tennis. On the center, eye tracking data, and on the right side, a little part of data that the demo behind me is also showing, where a camera directs itself according to the cinematographic rules and pose estimations. Thank you for your attention.
PDF. Ctrl L. Staat die micro aan? Of, no. Okay, can everyone hear me? I suppose this is working. Okay, so my name is Kristof, and I will be doing the final technical presentation of today, involving abnormal behavior detection and person re-identification. My presentation will mainly consist of two big parts. The first part, detecting abnormal behavior around railroad tracks, involves the conclusion of what my colleague Kristof Van Beeck started earlier. He did most of the talk about the person detection part of it, and I will be using these results to detect abnormal behavior around these railroad tracks. The second part of the talk will go about the start of a new case study involving camera surveillance in supermarkets and the detection of abnormal behavior there, which means things like shoplifting. In the first case, I will, of course, refer to the talk of Kristof earlier in terms of the data that we're working with. So the motivation of this entire case study was basically we want to detect when people are behaving dangerously around railroad tracks, danger for their safety or danger for other people's safety, which can involve running around on the platform or crossing the railroad tracks, which is of course strictly prohibited, but it's still being done way too much. Also, suicidal behavior is very important to be detected before it can actually happen. So we want to look at the patterns in movement of people around these tracks near the platform to see if we can maybe intercept this behavior. But of course, impulsive behavior is very, very difficult to predict. You can never really see or just look at a person and think, yeah, okay, he's exactly going to do this in the next few seconds. So this is very tough to define and acquire positive training samples, like when you just look at the camera images, then it's very hard also to say, like, yeah, this person at this moment in time, he is going to do something in the future that is completely abnormal. These movements can also be very erratic. The transition from normal behavior to abnormal can be very, very fast, as can be seen in cases where people suddenly run to another person and dragging onto the railroad track. It has happened before. And the detections and the trackings are not always accurate enough to precisely define the positions and the speed of the person to determine this. For our requirements, we want to make a distinction between normal and abnormal behavior, like I just said. And it has to operate semi-automatically or even fully automatically. Our goal is mainly to make the supervisor job, who watches all the cameras on the platforms, as easy as possible. So the questions we have to ask ourselves are, how much history do we need to track, for example? Like when you look at a person and he's walking on a platform, how long back in time do we have to go to see, to start seeing when he's going to behave abnormally? That is a big problem to solve. Also, the desired accuracy of this. Do we want to retrieve all cases of abnormal behavior and also retrieve some false positives, or do we want to limit ourselves to only detecting abnormal behavior and then maybe missing a couple of abnormal behavior tracks? That is also possible. And we want to make this program work in real time. so it can run on a system and give the supervisor real-time feedback. So for a small recap of the data we're working with, I'm going to open a video that Kristof already showed earlier. Yep. Oh. Come on. Doesn't really want to stick to the top of it. Yeah, like this. That's better. I haven't missed any relevant information yet. So here we have some persons being detected. This is on the annotated data, and they're crossing the railroad tracks, which is one of the types of abnormal behavior that we want to detect. I think they're gonna do this once more a bit later. No, they're just gonna appear there. But we basically want to look at these tracks that are generated by all detections belonging to one person, and then determining if the track is abnormal or not. Okay. Yeah. So on this slide, you can see all the detection tracks that we have generated from a lot of these videos, as I've just shown. These are from an earlier stage in our research process, where we haven't really used the YOLO framework yet, as Kristof already explained. So these were the tracks that we generated from them, but we were still able to work with them as a basis. So for every pedestrian that was detected, a track was created. When a person leaves the screen on the right side, for example, like here, and then goes this way and then re-enters that way, they are counted as two separate tracks in this instance. And for more information, of course, in your handouts you will find the presentation of Kristof Van Beeck, which explained this a bit more in detail. We are going to use an unsupervised approach for this, which means we are not going to label our data beforehand. We are going to make our system automatically learn what is abnormal behavior and what is not, without actually knowing beforehand what abnormal behavior is. The advantages of this is that labeling data is not really necessary in any case. So it's a very generic solution. And computationally, this is also usually less expensive than others, because it's more of more some kind of clustering algorithm rather than hard classification. But the disadvantages of this are, of course, that it's not nearly as fine-tunable as supervised solutions. And so we need to do this refining in pre or post-processing usually. The model we are going to use to define our person's behavior is actually pretty simple. It's a Markov chain. Markov chains are stochastic models purely defined by the transitions, or the transition probabilities between different states. Because we have only limited memory to work with, we only take the last n states into account, and the n, that's where the nth order Markov chain comes from. So when someone is detected at one location in time, you're only going to look n steps back in time to determine his future behavior. And because we're working with a finite state space like this, we're going to divide our camera view up into regions, because if you would work with all the pixel values as different states, of course, the model would be virtually untrainable. To divide our camera space up into regions, we are going to use a form of hierarchical clustering called agglomerative clustering. And we train this on the detections, or on a sample of the detections we have gotten. And then we train a k-nearest neighbor classifier around them to determine the rest of the points. So when you have a track that starts at point 1, point 2, point 3, like it's a bit difficult to see, but for example, this is point 1, point 2, point 3. They get reduced to just being in that region. So you get region 1, region 1, region 1 if you call this region region 1, which decreases the complexity of our problem immensely. Here is an overview of all the annotated paths overlaid with the regions. So instead of all the different small detections, we only have sequences of the different regions, and there can only be a maximum amount of values in the sequence equal to the amount of clusters we've trained on this. So of course we need to fit our Markov model to this, and we make use of the maximum likelihood estimation algorithm for this. And after training, this graph basically displays all the probabilities of the different tracks we saw earlier in the overview slide. And as you can clearly see, there are some tracks, like on this side of the image, that are much more improbable than the ones on this side. It's even a logarithmic scale, so you can imagine how drastically this probability drops. So we are going to set a threshold at some point, saying like everything on this side of the threshold is abnormal behavior, and everything on this side is normal behavior. And then we can evaluate this threshold with some data we've labeled. So here we again see an overview of all the paths that were used. And after only selecting the most abnormal ones with a certain threshold, we just keep these around. As you can see, most of the tracks or most of the paths where persons are crossing the railroad track, they are detected as abnormal. What is also curious to see is that the paths where people walk the entire length of the track, like here or here, are also detected, and this is very useful for us. I will explain why. Up to this point, we actually haven't really defined our evaluation criteria. Our algorithm is, as I said, unsupervised, and what actually is abnormal behavior in this case? In our data we received, there were also images of railroad workers who just walked along the tracks, but obviously you don't really want to count that as abnormal behavior, like, or maybe you do. If you want to evaluate the algorithm generally, but in this specific case, a railroad worker walking on the track is not really abnormal in a railroad context, while passengers suddenly crossing from the side obviously is. And in our data sets, we didn't really have a sufficient amount of actual suicides, luckily. But of course, that's problematic if you want to evaluate suicidal behavior. So what we did for this was independently, we labeled a certain part of our tracks as abnormal behavior, like we sat around, looked at the tracks and determined whether a path should be detected as abnormal behavior or not. So about 23% of the 154 tracks generated were counted as abnormal. Because we did this, we now also have actual true negatives to evaluate with. So we can use true positive rate and true negative rate instead of the more general precision and recall that is usually used for person detector algorithms, for example. In this case, true positives are paths correctly classified as abnormal, true negatives paths correctly classified as normal, and then you have false positives and false negatives. basically defined in the same way. So here you have the ROC curve that is generated by this, the receiver operator characteristic curve, where the ideal point is situated in this corner instead of this corner for the precision recall. This curve is generated on the earlier detections that we had. And we want to select an optimal point on this curve with a certain TPR and FPR. On this graph we have, for a TPR of around 70%, we have a false positive rate of 35%, which is not very good, but this is generated on the entire algorithm, including the detection step. If we if we visualize this, we see a high amount of false positives, the red ones. But while the pedestrian detection itself is accurate, the tracking of the pedestrians, like making sure that every detection point gets assigned to the right person ID, is not working very well, at least in this iteration of our algorithms. Like paths are being split up, or the tracking algorithm drifts away from its true location because of the Callemein tracking algorithm, just the way it works. And tracks IDs can, of course, be mixed up when persons cross each other. So the red curve in this case is basically our analysis on just our annotated data. So you're basically working from perfect detections or perfect trackings. And here we can see that our score is actually much better. We get for a true positive rate of 83%, we get a false positive rate of 28.6%, which is a quite nice result for an unsupervised classifier. And here is once again the visualization of this. So we almost only have green tracks and yellow tracks left. Still a couple of red ones, but yeah, these can't really be avoided with the amount of data we had to work with. So we can basically conclude that our system, in this case at least, is able to classify most of the paths correctly. And the results of this we published in a joint paper written with Kristof Van Beeck at the EAVISE conference in Lecce in Italy. There is another video I want to show you. If it wants to exit the presentation, but it doesn't really, like this, which is another data set we've recorded in collaboration with FLIR, where we basically try to create our own data set of abnormal behavior. Make sure this fits. Yep. So we went to Kortrijk and we pretended that this road were railroad tracks, and then we tried to act out certain scenarios of normal and abnormal behavior, and basically treating this as a railroad. As you can see, the data is pretty clear indeed. But the results we generated on this data set were a bit mediocre. And this is when we see it and plotted here, even with a rather high threshold, some tracks that should be detected as abnormal are unfortunately not really seen as abnormal. Like at the top here, I think you see a track crossing the railroad, but it's not registered as abnormal. But in this case, it's probably a lack of data that is hindering the algorithm a lot. We only had 19 tracks to work with on this camera viewpoint, so if we had more data, we probably would have seen better results on this comparable to the one on the previous data set. But I still wanted to include this, the discussion of this data set as part of the project process. So this concludes the first part of my talk. The second part will be about the start of a new use case involving companies Ceres Security and Carrefour for surveillance assistance in supermarkets. Our challenge here is to catch shoplifters before they actually manage to exit the store with stolen goods. And we want to do this by analyzing their behavior throughout the store. Shoplifters are apparently, according to the experts, very predictable. I had an interview with a site coordinator from Ceres, and he said the following quote: if a customer walks from the entrance of a store straight towards the electronic aisle, there's about 90% chance that they're a shoplifter, which is of course a very bold statement, but he was quite convinced of this fact. So if you ever go from the entrance of a store straight towards the electronic aisle, there's a chance that you might be followed by security, either by cameras or by an agent in the store. There are several criteria to determine if a person is suspicious or not. First of all, of course, the appearance, like if he's wearing sunglasses to hide his face from the camera, or he's wearing a backpack in the store where normally people really don't do that, or wear baggy clothes in the summer, things like that. Or the behavior of the person themselves, like when they walk through an aisle and look around very often, or they hide behind the shelves thinking that will actually protect them from the cameras, even though it just makes them more suspicious, and avoiding other customers in ways like eye contact. And the paths they take through the store, like I mentioned on the previous slide, are also a way to determine abnormal behavior and to separate normal customers from our suspects. And these pathways are actually a very important tool for the security guards, but it's also the hardest to supervise because security guard would have to track a person through the entire store without the person noticing him. And in the meantime, he can't really hold watch over the other areas. Here is a very simplified diagram of such a store with color codes determining how important the aisles are for, or the departments are for shoplifters. Like cosmetics, confections, electronics, and alcohol are very popular, while obviously dry foods and the fresh department are not very interesting for them. And here you can also see a simplified diagram of how cameras are distributed over the store. Like you can have a camera moving on a rail like this, or you can have dome cameras hanging on certain locations. So a security supervisor can only ask a client to display items which were clearly spotted as being taken, and it doesn't count as theft as long as the item has not left the shop without passing by the checkout. These are some constraints that the security guards have to work with, and is also something we have to take into account for our problem. The main causes of suspicious behavior here, is moving swiftly from the entrance to a popular department, as mentioned earlier with the electronics example. Going extremely slowly is also suspicious, because it's usually people who know the first rule who then try to counteract it by going very slowly and once again make themselves suspicious. And keeping watch near the entrance when they enter the store to see where all the security guards are also a dead giveaway. And here is an example of suspicious paths that people can take through the store, like going straight toward the electronic aisle, hanging around a bit, and then moving to the department next to it with, for example, cleaning and hygiene, hoping there is not a lot of cameras around there so they can store away their stolen goods in safety. Or when people move from the entrance to cosmetics, enter the dressing room with the cosmetics, enter them, exit them without these cosmetics in hand, but still running away with these stolen goods. So yeah, these are basically some kind of pathways that we want to detect and classify as abnormal. So when the security guards get noticed that someone is following one of these trajectories, that they can intervene accordingly. The problem in this case is that you can't really have a camera crew following one person around as soon as he enters the store. That's not really feasible and quite a violation of privacy. So we have to stitch information from multiple cameras together into one track for the person in the store. So when a person disappears in one camera view and reappears in another, we have to automatically link them together, see if they're the same person indeed. Which region did the person come from is also important. Like when a new person appears in a camera view, you have to know in which other camera he disappeared so you can reconstruct his path correctly. And the direction in which he's moving is, of course, important for the future predictions. We tried to tackle this problem at first with person re-identification with soft biometrics. What do I mean with these soft biometrics? When you cut out a person, you can calculate different features on him, like with a generalized color histogram or a segmented color for the head, the body, and the legs. You can use his height as a feature to recognize him in other camera views, and even the textures of the clothing can be modeled using things like local binary patterns, and then we use a weighted sum of these features in a smart way, even trained with a classifier maybe. You can use them to re-identify these persons in different camera views. Unfortunately, this approach failed quite drastically. As Kristof Van Beeck explained in his previous slide, background subtraction using a mixture of Gaussians or k-nearest neighbors, it can work all right if it's just people moving around, but once they stand still or there is something else moving in the environment, all detections get messed up quite hard. So we have to look to alternatives, like using the optical flow of the image or a more optimal use of a person detector even. And for that, we're going to look at a more deep metric learning approach. The architecture we're using here is from a paper published at CVPR in 2017. And it's based on faster RCNN, which was one of the benchmark or state-of-the-art person detectors in 2015, and it's still quite strong. The loss function they use here is called online instance matching, whereby every time you input new training samples into this network, you also update the description of the person. So yeah, basically you keep your identifier of the person up to date for every new training sample, instead of just keeping one stationary description calculated on one image. And this improves performance quite a bit. And what this architecture actually is basically a pre-trained ResNet 50 network, which is also used in faster RCNN, with a proprietary data set for the person re-identification part. Here is some more explanation of the online instance matching algorithm. So for every image, we basically have persons annotated, and we keep a certain feature vector for every person ID. And every time we get a new training sample with, every time we get a new training sample with the same person ID, the description we have of that person gets updated using exponential smoothing, which is generalized moving average. So it evolves in the time. And the unlabeled samples that are detected, like these persons, are not annotated with a certain ID, but they still get detected by the person detector part. They get labeled as negatives because, of course, they're never the same persons as these labeled people here. This form of training loss outperforms standard softmax loss in large-scale data sets where you have very sparse amounts of data for each class, which is what usually happens in person re-identification data sets. We did a couple of modifications to this algorithm. Basically, I tested this out of the box on the data set we had from series, but it performed pretty badly. At least the detection part already, it gave pretty bad results. So I switched up the faster RCNN detector for the YOLO version 2 framework, and already results were markedly improved. Then we add simple tracking based on the max cosine similarity between the base images and detections. And we also want to extend this online instance matching algorithm, which I explained, to the base feature generation. But that's still a work in progress and has not been completed for this talk to give any results about. So here is an example of how the tracking works. We have an image here from a camera, and we select a certain person, this janitor, that we want to track. And I will show the results of that right now. Yeah, like this. I maybe rewind it a bit because it's a bit annoying to switch this around. So as we can see, we just selected a person to be tracked, and it performs it quite accurately for the duration of this video and even further. So yeah, this is of course all based on a single camera, and we want to use this on multiple cameras. But that is also work for the future. But I'm quite happy that this part is already working quite well. Okay, back to the slides. Yeah, so the data set we received from series with the shoplifting surveillance is very large, but it has several drawbacks to do our training on. It is not labeled, it has erroneous metadata and a large amount of very useless footage that just films a back room somewhere where almost no people appear. So to evaluate our algorithm, we test this on a specialized re-identification data set. In this case, we use a subset of the Duke MTMC data set, formatted as similar to the market dataset, another re-identification database. And for this, we use 2,228 images with 702 identities. So here you can see some distribution statistics of this dataset. Most images have about 2 or 3 or 4 images of every person. So it's, as you can see, a very sparse data set that we're working with. So yeah, in this case, using precision recall or something else like cumulative match characteristic is not very representative because we haven't actually retrained this network on our own data set because we have no labels of it. So using these metrics is not very fair for the algorithm. Usually you take a certain part of a data set as a training set and then you perform your testing on another part of it and you don't really mix and match two entirely different data sets for that. So in order to still get some measurement of how well this performs, we calculated the cosine similarity score between the base image from one class and images from the other classes. We repeat this for every person ID in our data set, and we generate our score distributions. These score distributions are plotted here, and as you can clearly see, there is one very big outlier, and that is when you match two IDs together when they're actually the same person. So in the ideal case, we have as large a distance between these two as possible, with the red one, of course, being the average of the other distributions other than the outlier. Yeah, currently we are in this situation, which is a nice start, but we want to increase this distance. And for that, we are going to look at some more characteristics of this. We go measure how much the distributions differ from each other. Ideally, we want to maximize the distance for every zero offset score. A zero offset score in this case is when you match an ID with the same ID. And we want to minimize the distances for every other offset score, like when you match an ID with the same, with the ID plus 1 or plus 2 or plus 3. And for that we get this graph here. This measurement is also called Kullback-Leibler divergence. This Kullback-Leibler divergence is closely related to what cross entropy loss does, but it's subtly different and has been used as a loss function before in certain architectures like SVM or even GANs. But for deep metric learning, I haven't really found a lot of literature involving this loss function, and I still think it's quite interesting to maybe investigate this a bit more. So yeah, the further proceedings of this use case, of course the VIPER project has now finished, but there's still a lot of work that can be done with this once we have our re-identification stage solved. We want to expand this to work as well as possible in a multiple camera setup, and for that we also have a master thesis or even several master theses running at the moment. And as I just said, exploring the properties of this Kullback-Leibler loss or Kullback-Leibler divergence in a ReID context is also something that we could look at in the future. And once we have our actual path reconstructed, we can finally train a model predicting the shoplifting behavior. But that is, of course, future work. So that concludes the final technical presentation of today. I think Professor Vennekens is now going to give a concluding presentation involving future proceedings and how the work of the VIPER project can be used in the future. Thank you.
So to finish the symposium today, I will now present you a quick commercial with some advertisements for our ongoing and upcoming research projects. So as by now you probably already know, the mission of our research group is to help new technologies cross this so-called valley of death, where a lot has been already invested in the technology from fundamental research, but it's not yet up to a point where industry is willing to start investing in it. So what we do is we typically do application-oriented research aiming at helping technology get across this gap, and we do this for technology from the areas of computer vision and artificial intelligence. So given that that's our mission, obviously we like to collaborate with industrial partners. We do so both in the context of bilateral projects, so that means that a company pays us to do some research, either they pay us using their own funds or from some subsidies that they can receive from the government for this. Or we also collaborate with companies in the context of technology transfer projects, such as the VIPER project, about which we've already been telling you the entire afternoon. So there are a number of projects that have recently started. So in October 1st of this year, we started 2 new technology transfer projects, one about time series analysis, another about decision analytics. And next year, we will also hope to start a project on starting to deep learn and something about embedded hardware for real-time neural network inference. So these projects are technology transfer projects, as I said. So very quickly, the idea of such a project is to take some new technology, that means technology that is currently not yet in use in industry, or at least not in the Flemish industry, and that we do 2 years of research and valorization activities that are aimed at helping companies, and in particular Flemish SMEs, to adopt this new technology. An important role in this project is played by the user group of companies. So those are companies that are especially interested in the project and that help to steer the project, that typically provide some use cases or case studies. So you saw in the presentation of Toon at the start of the day, you already saw, for instance, the user group that helped to guide this VIPER Tetra project that we are now finishing. So a bit more in detail about these upcoming Tetra projects, or the ones that are already ongoing. So the first is a Tetra project about time series analysis, where the goal is simply that companies are starting to collect more and more data. A lot of this data is in the form of time series, and we want to see what kind of algorithms and what kind of technology can we apply to this data in order to get some useful intelligence out of it. Typical examples of the kind of data that we want to handle, well, the classical example is that you have some sensors on some machine and you are just logging the output of the sensor, so then you have this analog sensor data. Another application is you have some kind of computer network where messages are being passed, for instance, and you keep a log of all of these messages, how big they are when they are transferred and how long it takes to transfer them. And a third kind of data is geospatial data, where you have, for instance, a GPS tracker that is following some people or some objects around, or you have some camera footage, such as the case of the supermarket surveillance that we saw earlier. And you use this to track the persons or the objects, and you want to arrive at some conclusions based on the way in which, for instance, a customer is moving across a supermarket. The kind of things that you typically want to do from this data, well, the very classical example is forecasting. So you look at what happened in the past and you try to predict the future. For instance, you want to predict whether the price of a certain stock is going to go up or down based on what it's been doing the past months. We probably won't be looking at that particular use case that much in this project. We want to focus more on anomaly detection or anomaly prediction, where you want to detect whether things are about to go wrong. And preferably you want to detect this slightly before, for instance, one of your customers is going to run into this problem, so that you can fix it without anyone ever having to know that things were about to go bad. Other tasks are, for instance, pattern recognition. You want to monitor, for instance, the electricity usage in a home and use this to decide when someone is turning on or off their washing machine. So that's the kind of tasks that we want to do. So that's our time series project. A second project that's also already ongoing is the project about decision analytics. So that's something else entirely, completely different context. Here we want to take a look at decision processes that are typically happening in companies. So in every company, a lot of decision processes are going on, and often these aren't very well understood. So you know that there's a decision, and you know that there are certain people who make this decision, and this can be either high-level strategic decisions or everyday operational decisions. And often it's not quite clear how precisely this decision process is happening. What precisely do the people look at, and when do they decide one thing, when do they decide another thing? So here in this project, we want to look at technologies and methodologies that you can use to come up with a formal representation of these decision processes, such that once you have this representation, you can apply various inference algorithms to it in order to, for instance, automate or partially automate the decision processes, or to analyze them, to optimize them, to find out things, for instance, that are missing from these decision processes. So this decision analytics project is in collaboration with people from also the Faculty of Economics from KU Leuven, who are also interested in this, but from a more economical perspective. Then the Start to Deep Learn project. So as you could already tell from the previous presentations, if you look at what is currently happening in the state of the art in computer vision, but also in other areas of artificial intelligence, you basically see that deep learning methods are beating everything else, and often quite substantially so. So the big idea of deep learning is to use neural networks, but not the neural networks that have been used over the past 30 years, but deeper neural networks with more layers, so that you can kind of cut out the middleman, and you no longer need to have a domain expert who defines which features you're going to use, but the neural network learns itself what are the important features. So given that these things are outperforming everything else by huge margins in certain specific areas, more and more companies are also getting interested in this stuff. But if you want to get into deep learning, then there are, of course, a number of questions that you need to address. And so in this project, we want to help you do this. So we're going to look at case studies from a number of different domains, and we're going to look at the kind of questions that people typically have, such as which of the numerous frameworks for deep learning that are out there is the suitable one for this particular case study, which hardware is well suited for running this often very computationally intensive tasks, how much training data do you need, because that's often one of the big bottlenecks, that you need huge amounts of training data. One way to get around this need for training data is if you can reuse parts of existing networks, as was also mentioned in the previous talks. So then we're talking about transfer learning, so that's something that we also want to look into. And then, of course, once you have your proposal, this is the kind of technique that I want to use, you also need to be able to evaluate the performance. So you need to see how well the network is actually doing. So those are the kind of questions that we want to help you in our Start to Deep Learn project. And the final project that I want to tell you about is the project about embedded hardware for real-time neural network inference. So this is basically zooming in on the topic of inference, of doing these very complex computations in an efficient way. And here we want to look at how different kinds of hardware can help you do this in an efficient way. So we want to look at GPUs, also embedded GPUs, FPGAs, etc. And we want to ask, for instance, how can you optimize your given neural network for these specific kinds of architecture? Which high-level tools can you use to avoid having to do all this kind of very low-level manual fine-tuning? And again, we want to do this using various use cases from different areas of computer vision. Okay, so those were some quick, very quick overview of some of the projects that we're doing. So as you know, we at the EAVISE group like collaborating with industrial partners. These Tetra projects that I mentioned are projects where we're still actively looking for companies to come and join the user groups of these projects. And in addition to that, we're also always interested in seeing whether we can set up some kind of bilateral collaboration where we do something specifically for your company. If you might be interested in this, then feel free to shoot us an email. You can, of course, also keep track of the activities of our research group online, follow on our website. And final thing that I want to mention is that when you came in, you also received a feedback form together with your registration documents. Please fill in this feedback form where you can tell us how you like the symposium. And if you might be interested in joining one of our projects, you can also indicate this on the feedback form, and then we will get in touch with you. When you leave the building, you can deposit this feedback form into a box that you will see there. Okay, thank you.
Thank you, Joost. I only take the microphone just for two small announcements. One of it, I get a request often of the availability of the slides of this seminar, of this symposium. Well, they will be available on the bottom URL in PDF format, and all the videos will also be available there to show all your colleagues and friends, like what you've been doing this afternoon. One other announcement is for the students that are following this course in the scope of the seminar course. We have a form here on which you can mark down your pleasantness and sign it with your own signature, such that we can keep track of how many hours you have been following in your seminar course. So that ends this afternoon. I hope you all enjoyed it. I did. Please have a look at our demos. They're still available. I don't know if there's still coffee or water left, but thank you very much for coming here, and I hope to hear from you soon.